Good afternoon, ladies and gentlemen. Can I offer you a very warm welcome to the physics department as part of this alumni weekend. It's great to have so many people here for what I hope will prove to be a very special event. So this is Baking a Cake, Physics in 3 Layers. Now, one of the things you might be asking is why are we holding such an event in a physics department? And one of the reasons is because of Nicholas Kurti. He was a physicist who was here at the department, spent most of his career here, born in Budapest. He was one of that generation of physicists who came from Germany and exiled in the 1930s. In 1933, he, along with a number of other German refugees, came to Oxford as part of a scientific package which included Einstein and Schrödinger and a whole series of other physicists. And Curti spent his career here working primarily in low temperature physics. And actually his arrival, together with that of other German colleagues, turned Oxford into a centre of low temperature physics because they brought all this expertise that had been developed in Germany. We were the first place in the UK to have liquid helium, which allowed access to really low temperatures. So Nicholas spent his career here. He was the first person to achieve temperatures well below 1,000th of a Kelvin, above absolute zero. He also had a technician called Martin Wood, after whom this lecture theatre is named. Martin Wood didn't invent the lecture theatre, but he developed superconducting magnets and founded Oxford Instruments, which is one of the world's leading suppliers of superconducting magnets, and its successor has ended up being the main manufacturer of MRI magnets. If you ever have an MRI scan in a hospital, you've probably been inside one of those magnets that came from the work that you can trace back all the way to Curti. But Curti had another interest, which was cooking. He was really interested in cuisine, in making dishes, and he wanted to use his physics and his scientific understanding to improve that. So he, together with another colleague, coined the term molecular gastronomy, and they influenced all kinds of chefs like Heston Blumenthal, and he worked with Raymond Blanc. And I can remember here in the physics department, when he was in his very late 80s, him giving a lecture about the physics of cuisine. So we've had this tradition of linking physics and cookery together. And this made us think, well, how can we keep that tradition going? And we've, for a long time, been wanting to put on an event which connects physics with science, but who to get to do it? And of course, like many of you, I was watching the Great British Bake Off during the pandemic, which was a great solace in difficult times because it carried on and it brought this sort of sense of normality. And very often they have a scientist as one of the contestants, but you will probably remember in 2021, one of the contestants, a scientist, Jürgen the baker, I think struck me and many of us, I think, as not only being an amazing cook, but the way he explained how the baking process worked was absolutely astonishing and really very inspiring. So we wondered whether he might be interested in coming along to do us the honour of explaining something about the physics of baking, and we're absolutely delighted to have him here. So please would you join me in welcoming Jürgen Krauss. So Jürgen, how will we start today?
Well, first of all, thank you, Simon, for inviting me. I would never have expected to be in a lecture theatre in Oxford on this side of the table. It feels like truly standing on the shoulders of giants being here, or is it rather tumbling into the footsteps of a giant? So I'll try to do Nicholas Kurti justice, and we'll see what comes out of it. When I was looking for something to demonstrate here, I had a few ideas, but the idea that stuck with me as a scientist as well is very much about the importance of failure. So I chose this cake that I just couldn't get done. And being invited here gave me gave me an impetus to do research. Why did it happen? Why did it go so wrong? It's a traditional German recipe, hundreds of years old. Lots of housewives have done it. Lots of housewives are shying away from it. So there it is. The name is derived from a garment, from a medieval garment. It's called Schecke. It was very popular in Eastern Germany around 1480s, 90s. Worn by men, it divides the man into three parts. There's a belt, there's a top part, there's a bottom part. So the cake has three parts. Now, this garment has a problem, quite a big problem, and some German towns have laws to deal with this problem. Well, you can't attach your leggings to the belt if you have something that goes lower than the belt. And so it came to exposures, I suppose. My cake has a problem. The cake I'm talking about has a problem. It's called Eierschecke, so it's a three-part thing which has a lot of eggs in it. And, well, the problems, I'll talk about those later. It just didn't work out. The bottom part is essentially a sweetbread, a yeasted cake. The middle part is something like a cheesecake, and the top part is something like a souffle. So very unlikely partners in something you want to put in your oven. And I thought we'd start with the bottom bit of it. And the bottom layer is essentially a bread. Here are typical bread recipes. To the left-hand side, you see a normal white bread, which has mainly water and flour in it, a little bit of salt, a little bit of yeast. In the middle is a typical brioche, where part of the liquid is substituted with egg and fat. And to the right-hand side, that's our base. So you could say it's a poor man brioche, just not as fatty. But you see the similarity. Everything has flour and some kind of liquid as the main bits. So why does bread need liquid? Well, strange question. As soon as you put liquid onto flour, the chemical reactions in the bread start going on. Water interacts with starch, and water interacts with the proteins that are in your flour. If we look at a typical flour bath, this is bread flour, probably says about 14% of protein. The rest of it is starches and a tiny bit of minerals. Those 14% protein, they contain different things. The two main groups of proteins we're interested in are gliadin and glutenin, and they together with water make the gluten, which has rather bad reputation. But it is a scaffold that holds everything together. So we'll have a look at how that works. Now I'm going to mix water and flour to make some gluten, which is interspersed with starch. And once I've done that, I would like a volunteer who is willing to get their hands dirty. It will be a task of about 20 minutes hard labor. And short sleeves would be good. Okay? Lady? Or up there? Girl?
Please do come down.
Please do come down, yes. It doesn't need much power, it just needs a bit of patience. So here I've got my water and I've got flour, 500 grams of flour and about 330 grams of water, the typical ratio for bread. As soon as the flour gets moist, glutenin and gliadin will form gluten. We go into the details later. But don't worry, just wanted to ask, how many of you are physicists? Hands up. Quite substantial. How many of you bake? Oh, Oh, more physicists than bakers. Interesting. Okay, I'll keep it for the bakers. Let's see that. So water reacts with the flour. Water hydrates these two proteins, and well, this hand is still clean. Throughout this lecture, throughout this lecture, we deal with things like that. When we put water into flour, this kind of thing happens. The ball unravels. This is gliadin unraveling. It gets longer. And the same will happen with starch when we heat it. And the art of cooking is nothing other than understanding how it unravels and how we can keep it unraveled. And that's all this is about. I should also say that you all have received the recipe. You might be tempted to meticulously follow the recipe to understand what I'm doing. I shall say, don't bother, because this cake takes so long to make, I won't get it done here. So I'll talk about the parts, and the first part I'm talking about is the gluten, bread dough. So in order to unravel these molecules, we need to attack the chemical bonds. Now, water is very good at attacking these chemical bonds that play a role in keeping our ball of wool together. Within this ball of wool, hydrogen atoms attract each other, and there's also another bit, a very special part of protein that contains a sulfur atom. And water kind of takes one of that hydrogen away that's attached to the sulfur, and that sulfur will find another sulfur on a strand. So that's the mechanism how this ball of wool stays a ball of wool within dry flour. When we add water, these bonds break, and the sulfur will find another sulfur on a different strand of gluten. So the whole thing unravels, but starts forming a network. And that's what I'm doing here now. It's not just the water that unravels these chemical bonds, it's also shear forces, especially shear forces. So if you stretch the dough, that shears the molecules inside, and that unravels these bonds. The strands get longer, they find their bits. The other protein comes in as kind of an intermediate between two of these longer strands. So the whole thing builds a complex. Another side effect of this sulfur bond is that it repels water. So that's why a dough starts feeling drier when you knead it. That's a sign of gluten forming in there. I'm coming to you very shortly. So we have shear forces, mechanical by kneading, but it's also time. If you just let it sit there, these bonds will break, and part of the gluten will curl back onto itself. So in baker's terms, we talk about the gluten is relaxing, the dough is relaxing, and it starts feeling soft again. We then can knead it again, or fold it over, or knock it down. There are many ways to describe that in baking language. But what that means is that we take this loose structure, which has more connections, more network than it had before still, but is loose, and we stretch it, and we organize it in long strands or sheets. And the more we do that, the more air can be trapped within these gluten sheets. The air or gas comes in via yeast or sourdough, and that's why well-processed dough makes nice bread, essentially. So it stops getting too sticky, still a little bit sticky. But I mentioned at the beginning that this flour has about 14% of protein. Whoops. And the most part of the protein will have formed gluten by now. So we have got flour, we have got water in here, we have got gluten, and then we've got starch. Gluten sounds very abstract. If you look at things like that, you can't really imagine what it looks like, what it feels like. And you touch bread dough, you don't touch gluten. Now, that's where you come in. What's your name? Anna? Good. So you will show us gluten. Turn your arms up, your sleeves up, please. And we'll do something you probably won't do at home. It's very messy. And if the water gets too messy, you can ask for fresh water, okay? So what you're going to do is to wash out the starch, and just the gluten will remain. It will be smaller than this ball of dough, and it will have a very interesting structure. So it is something we just don't see at home, because who on earth would have an idea to do something like that? So you dip it, you squeeze it a bit, you fold it over, and make it again stick together. Does that look interesting? And then when you think it holds together and doesn't fall apart and so on, then you give it another dip. Squeeze it a bit to get the starch out. You see the water is already getting quite white. That's all wheat starch coming out. And there you go. And it takes a while to get to the stage where no starch is running out anymore, 10 to 15 minutes, I would think. Thank you very much. So that's the water and the flour, two main ingredients out of the many ingredients in bread. Thyme, I mentioned as the other big ingredient. Now we look at what else goes into our base. And for that, we need to look at the whole process of making bread. Weighing out the ingredients, that's an obvious one, although not so obvious. Nicholas Kurti was very adamant in his lectures that you should weigh everything and possibly use metric measurements. I'll come back to the weighing later. The next step is mixing, which we have done, putting water and flour together, and whatever else goes in. Kneading is kind of sorting out the structure of the gluten. Resting, we addressed in that gluten bonds break, and they then can be realigned in the next step. So resting is very important. It also gives yeast or other raising agents time to act. Then weighing out the dough pieces. If you are in a bakery, you make a huge slab of dough, and you'll cut pieces of that. In bakery books, the weighing out pieces is always important. Otherwise, you might end up with something that doesn't fit into your oven. Pre-shaping means you just shape your dough pieces in something that's easier to handle later, usually a bowl or some kind of log. And then if you make 20 pieces of bread at once, you can't all shape them at the same time. So bakers call that a bench rest. It also allows the gluten to relax after pre-shaping, to then have a better way to shape, a more precise way of shaping your rolls or braids, whatever you want to do. Shaping is bringing the dough into its final form, the final proof, resting the dough in its final form, and then baking, and important cooling. During baking, the starch gelatinizes. The cooling allows the starch to set a little bit. If you cut hot bread, it looks a mess. So these are the phases of making bread, and resting is quite a big part of it. And that's essentially what I'm going to do here with this slot. I will demonstrate with whatever goes into our cake base how these ingredients individually affect the dough. And because this is a scientific audience, they might be aware that nothing might happen and the experiment might go badly wrong, but it should all work out. In our cake base, if you remember the previous slide that compares the 3 bread types, in our cake base we have flour, fruit sugar, we have yeast, we have salt, we have milk, egg and butter. I won't do the milk bit, but I will do all the other components. So I'm just starting off with 200 grams of flour, 3 grams of instant yeast, and 130 grams or so water. So this will give a saltless dough, which rises. I will knead that to some moderate gluten development and then let it rest. And during the rest, I will do 5 more of these. If you have any questions to what I've said so far, please ask me or Professor Blundell, and we'll be glad to answer. So, rolling the dough like that also exposes the dough to shear pressure, shear forces. There's many ways you can apply shear forces. Some people roll it like that and then that, or stretch and fold over. There's many ways to do that. Some work better with dry dough, some work better with wet doughs. For this kind of consistency, I like this one. There's also the one I did on Bake Off quite a lot, which is slamming it on the floor, on the table. This is not enough dough to do that. So this should be enough for number 1. Now at home I would cover that because you don't want the surface to dry out and a skin to develop on your dough. That will stop it from rising. Here I just leave it on the table because we're working quite quickly. I also put in quite a lot of yeast in order to get a reaction from the dough during the allotted time during this talk. So number 2 is your typical French white bread. That is yeast and salt.
Yes, yeast and salt.
And oh my, I've got it all in the same pot. Don't put yeast and salt together, I've heard. The reason why I can do it is it's dry yeast. What do dry yeast and salt do together in a pot? Nothing. They're both dry. There's no water to start a chemical reaction. If you put salt on fresh yeast, the salt will pull out water from the yeast cells, and the yeast cells die and pop. And it's quite impressive to do that experiment. I haven't got fresh yeast here, unfortunately. But you can see the yeast die, and it's a heartbreaking thing.
So experiment 1 was flour, water and yeast. This one is now flour, water and yeast and salt.
That's right. So I mentioned that the salt attracts water or needs water to dissolve. This water, of course, is not available to the yeast and is also not available to the gluten formation. So the dough will feel a bit stiffer. So salt strengthens the gluten in that way.
So why should salt not be stored with yeast?
Fresh yeast.
Fresh yeast,
Fresh
right.
yeast. Yeah, I was just about to come. Is it getting a bit messy? just let me do a bit of magic. Usually, if you touch dough and you're a bit slow and timid, the dough will know that. It's highly intelligent. It's an incredible structure, gluten and flour and all of that. They know when you're worried and afraid of it, and it bites back. It bites back by sticking and falling apart. And you've already done an amazing job here, I have to say. You can see how elastic and gum-like the whole thing is. So we need to just align all this loose wool to give it a bit of strength. So if you continue with that, is that okay? Just continue folding it over a little bit more before you wash it again, and we'll have someone get fresh water. Is that okay? Good. All right. It's very sticky, isn't it? So I'll carry a few grams of gluten over to my bowls, and we'll do number 3.
So you're never going to volunteer for anything again, are you?
Now, I would like another volunteer. Okay, this lady is very eager. So my number 3 is flour. I won't put salt in to keep it a bit more scientific. Nothing I'm producing here will be really edible, so it doesn't matter. This is flour, this is the pure amount of yeast, and then butter. That's 20 grams of butter. Please, maybe on the other side. And the amount of water. So what I would like, your name?
Ella.
Ella. Mm-hmm. So Ella, what I would like you to do is just to tap these balls of dough and tell me what you feel.
Okay. Resistance?
Yeah.
Oh, but more on that one.
More on that one.
This one's stickier.
It's stickier?
Yeah.
Yeah. So one had more time to dry, but there's clearly more resistance in one as compared to the other.
Yeah, I think this one.
So we'll keep doing that for the other 4.
Okay.
If you wouldn't mind. Thank you.
So you're going to be our resistance meter.
Okay.
So my fingers were a bit sticky from the other gluten experience. I need my most important tool. This was in the famous tent with me. It's the best thing you can ever buy when you're making bread, because you can use it to clean your table, you can use it to pick up your dough, you can use it to fold your dough if you need to make something very wet like focaccia. You can clean your hands. You can cut your dough to slice, to measure your pieces. So. Now this has 20 grams of butter in it. Which is about 10% of butter on dough weight. Bakers also professional bakers talk in percent, and a typical bread has 170% of ingredients. Any problems with that? Maybe the physicists. the thing is, flour is always 100%. Whatever flour you put in, it's 100%. And all the other ingredients are given in percentages of that. So I've got 100% flour, 200 grams flour, 20 grams butter, so that's 10% of butter. 135 grams of water, that's something like 68% of water.
No, we don't know what 90% of the mass of the universe is, so I think this will be 110% will be fine.
Yeah, I think we have come a long way since Curty. We know more about the atmosphere of Venus, and we know a lot more about the interior of soufflés.
Yes, that was his. Yes, that was his famous quote.
Yeah. So I'm folding this over to give it some strength. These ones had time to rest, so I'm just folding them over to give them sort of a similar treatment. Remember, time, gluten bonds break off, and you need to fold it over, reshape it to rearrange the gluten in sheets or strands. So could I ask you to do the honors again, please? Which one would you choose as a mattress filling?
I think this one's softer.
Yeah.
The third one's softer.
Yeah, so that's the fat.
And it spreads out more. This is more like elastic. It's like springing back
Yeah,
more, this one.
Yeah. So salt provides a stronger gluten structure. Fat works the other way around. It makes it more tender by kind of wrapping around, encasing the gliadin and glutenin molecules in a water-repellent layer, so less gluten can form. When you knead it, you will form these gluten sheets, but there will be less than in a bread dough just with salt or without anything. Now, this can inform our process of making a cake base. It's a question of when to add the butter. If you add the butter at the beginning, you won't get long gluten strands. The dough stays short, as the bakers say. You get more a cake-like structure. If you develop the gluten to something like here, springy and well developed, and then you add the butter, these long gluten strands stay in place, and the fat kind of sneaks in between, and you get something like brioche. Next one. Oops. Next one is yeast and sugar.
Oh, okay. Cool.
So sugar, again, is hygroscopic, so it attracts a lot of water to dissolve itself. And again, that water isn't available to the yeast and to the gluten to form strands. Sugar, of course, is food for yeast. That means we might expect a slightly faster rise of this one. In terms of the gluten development, sugar, as the sugar gathers water from the beginning, the dough should be somewhat stronger as well. But the sugar gathers so much water that the dough actually feels wet and sticky. And with sugar, it starts getting really complicated. So sugar helps yeast to grow very fast, just providing a lot of nutrition. That means there's a lot of yeast cells that die pretty fast. And dead yeast cells, any idea what they do to dough? They snip starches in bits, and they also act against gluten. So it's kind of counterproductive if you want to make a voluminous loaf. But if you want something like a croissant where you have to pull your dough a lot, this is very helpful. So there's instant yeast, which hasn't got dead yeast cells. And there's dry active yeast on the market, which is active yeast contained in dead yeast cells, precisely for that purpose. The baker's term is extensible. With dead yeast cells, you get an extensible dough because gluten gets attacked by the dead yeast cells in some way. The dough gets extensible, and with salt, the dough becomes elastic. So, two very different things. Again, knowing about how things work on a small level can inform which ingredients you choose for a specific bake. So, please.
It's stickier.
It is sticky, isn't it? Yeah. If you imagine making a braid, which dough would you choose of the four?
Well, from my wealth of experience,
Never mind.
I would say this one.
That one.
The first one.
Uh-huh. Yeah, interesting.
No sort of shorter, right?
Yeah, no.
Is that interesting? Yeah.
Yeah. It's the one that sits kind of in between everything because you get the pure structure of the flour. So it feels softer and more extensible than the one with salt. But it feels less extensible than the one with fat or sugar, if that makes sense. So
And it's the fat that makes this one spread out more.
it is, yes. The next one is egg yolk. Oops, that had to happen. So, okay, egg yolk. Egg yolk is about 18 grams, so it's a similar amount again as fat. And with egg yolk, it really gets complicated because you have fat, but egg yolk is also 50% of water, so you hydrate the dough more. And then you have got lots of other enzymes in there that do all sorts of things. You have got amylase that breaks starches down into sugar. You have lecithin, which is a tenderizer for gluten. So you get a whole spread of effects. And of course, you get a nice yellow color of the dough. Does this all make sense so far? Any questions?
One question is relating to the experiment we have over here. We might be reaching the law of diminishing returns, I think.
Oh, yes, it has got quite small, I see.
It has got quite small.
Yes. Sorry, that slipped my attention. So we'll leave this here. I look after that, and then I'll fold them, and you can do another test. So something got lost. That's fine. That looks absolutely great. I'll just wash my hands in this starchy sauce. Okay. So I'll try and give this a nice structure now. If you want to wash your hands.
Also, if you...
Or that. Yeah. So she's done a wonderful job here. Something like kneading jellyfish or so, really not an everyday experience. Thank you so much. I'll take this over here, closer to the camera. I'll stretch and fold this piece of almost pure gluten now. And we should have something elastic, well-shaped. I've got a bit torn. I'll just let it sit in this for a while. Let time do its thing with the gluten, breaking up bonds, recoiling, and then we'll fold it over again. So again, this is a time should help us structure the gluten, and we'll carry on with this. So
yeah, this is an experiment you can all try at home as well. I'm sure everyone will be.
yeah, it's great fun.
Yes.
This one's wetter. Is that
Probably
maybe the
because
water on
I
your
touched
hand?
it, yes.
Shall I turn it over? Stronger?
Yeah,
Stiffer, maybe?
yeah,
Yeah, and more resistant.
yeah. So knowing what goes on in egg yolk and dough and these interactions really makes it complicated. I hope to see a difference in the crumb once we bake it. Or also during the rise of these breads, we should see some bubbles through these beakers. Last one then is egg white. And I'll try to just add about half of it, which, well, that was all of it. So egg white contains a lot of water and a lot of another protein called albumin. And that's a very important one for pastry. I'll come back to that later when we discuss the topping. But I can say that much, that it provides a scaffolding, a strength to pastry goods. And it also does that with gluten. It's a stabilizer. So in terms of scientific experiment, this has a bit too much liquid in it now as compared to the others, but hope you won't be too critical. So, number 6. Of course, these have skins now. I can just fold them over again. If you use this technique at home, you actually don't have to knead bread. You just mix water and flour and let it stand, and then you do this folding as I do with these ones here. 1, 2, 3, 4. You wait for 20 minutes, do it again, do this about 4 or 5 times, and you have the most beautiful bread without shedding any sweat or hard labor. So. So I've given them all the same folding treatment. They all have had time to relax. This last one, not so much, but one last time, would you please have a look?
It's softer than the last one.
Yeah.
And much like stringier.
Yeah.
Sticks to my finger more.
Yeah. So if we tear that, try to tear that, we can pull quite a bit away. This one there is easier.
And this one breaks like suddenly, whereas this one goes stringier and then.
Yeah, so there has been an effect on the gluten structure with egg white.
Thank you.
Okay, thank you very much.
Thank you.
So, the foil. Okay, I'll put these into these jars now, and we can watch them rise during the rest of the demonstration. Number 6, I will also bake them in these jars. Number 5, we should be able to see through the glass what kind of bubble structure develops inside. 4, 3, 2, 1. Just to cover them so they don't dry out. And then I'll try to get our ball of gluten to a state where we can see what gluten is all about. A German word for gluten is Kleber, which means essentially glue. Well, very similar to the English word or to the scientific word. That's what it does. It sticks the starch together. When we bake the bread, the starch and water react. During heat, during the application of heat, the starch chains unfold. Something similar like in the proteins with gluten and gliadin happens. These starch molecules that can have branches or not, they line up and form larger networks that are elastic. And you get things like jam or glazes on cakes also. Good, this can go. Let's quickly try and give this another go. It's not so easily torn apart anymore. So networks have reformed. It feels softer than it was before, right after washing, but it feels also more connected.
So just those few minutes sitting in that pot have been enough for the connections to start to reform.
Yeah, and that, of course, happens in bread as well. So if you leave bread to sit around, this is what's going on inside. And this sort of thing will trap gases, which are important for the rise. So when you bake bread, there's several mechanisms that make the bread rise. One is, of course, yeast or sourdough bacteria produce gases while they get warmer in the oven until they die. And they fill up these bubbles. And then you have water in your dough, which evaporates and also contributes to the volume of those bubbles. Yeah, and a good structure is certainly helpful with that. Essential, actually. So I think we are at a point again where we should let it rest, but I'll try and do another tearing experiment here. So it's almost like this special glue you buy your kids. Quite fascinating. Could go on with that. Would anyone like to touch it? I'll keep it here. So, okay. That was the bottom layer.
That was the bottom layer. So we're now moving up to the middle layer of this cake. And as we see here, it's quite similar to a German cheesecake, isn't it?
Yeah. It is essentially a German cheesecake. There are so many variations of German cheesecakes, different recipes. Some contain beaten egg white, etc. This is rather simple. Our topping, our middle layer just contains milk, a little bit of egg yolk, starch, sugar, and quark. Now, quark is a...
Yeah, this is an audience of physicists, so we think everything's made of quarks. But,
Yeah. You would say we need 3 quarks, but we only need 1. Well, actually, top, bottom, and what's the third one? Okay, quarks are known to be a building block of matter. So they're a building block of city walls as well. And they knew that. They knew that in the Middle Ages in a town called Freiburg, which is very close to Dresden. The cake I'm talking here about is from Dresden. In Freiburg, well, they used their quarks to build their city wall. Quark, which is a byproduct of making cheese. So essentially all the casein goes in there. Typical German quark is very dry and fat-free. So yeah, it's this indigestible polymer you made buttons of, etc. And in the Middle Ages, they knew it was also a good building material. They mixed it into clay, I think especially in places where there was no chalk. So this town, Friedberg, they wanted to make Eierschecke, as we do here, but all their quark was used up in reinforcing the city wall. Therefore, there's a Friedberger Eierschecke missing the middle bit. But we will use our 3 quarks in the middle layer. Another part which is not in this recipe comparison is pudding. Now, in England, pudding means something different, but in Germany, pudding is something rather strange. You buy it in sachet. Lots of baking things in Germany come in sachets. So you buy a sachet of baking powder. In Germany, there is no self-raising flour. So British people going to Germany scratch their head. We Germans coming to England scratch our head about self-raising flour. In Germany, you buy a packet of baking powder, and that's 16 grams of baking powder. From 100 years ago, you can use these recipes, 1 packet of baking powder, 16 grams, it works. Pudding is another powder, which per packet is typically 35 grams of cornstarch and some flavorings. So why on earth would you pack this up? I think it just looks more attractive. If you say you cook your milk and starch and make that a great dessert, I don't know. It doesn't sound that appetizing to me. I've made some of it. And that's what it looks like. It's firm enough that you can turn it out onto a plate and serve as individual portions. So many German cheesecakes have this as an ingredient. So you buy a sachet of pudding powder, you cook it with your milk, and this is what you get. Would you like me to see making a portion of pudding here?
Yeah.
Okay. We need a pot. We need some scales. There we come to measuring. Nicholas Kurti said, measure everything, and I would subscribe to that. I usually measure my egg whites and my egg yolks with a scale. I know the typical egg yolk has 18 grams, and the typical egg white for medium to large egg in the UK has 40 grams, but not always, and especially in making small amounts of food or a huge quantity. If you count the eggs, you end up with something different. There's milk. So we'll make some nice vanilla pudding. Vanilla pudding was my favorite. My brother loved chocolate pudding. Sometimes it was a meal after school. In Germany, there's no school meals. Well, when I was little, there was no afternoon lessons. So we came home after school and had our lunch at home. And pudding is a very quick thing to do. Just heat up some milk and a powdered pack, which is all the sweetness, and then a bit of sugar, and that's it. We need our starch, and I need my recipe. So, for this amount of milk, 700 grams of milk, I need about 50 grams of starch and some sugar. Now at home, please don't do what I'm doing now. Always weigh into separate bowls. "40 grams of sugar, and then we also need some flavoring, vanilla bean paste, and for this amount it would be about 2 teaspoons or something like that. So when you cook starch, you have to be careful that it doesn't create lumps. So the standard procedure for making pudding is you pour a bit of your cold milk into the starch mixture, whisk it up, while your milk heats, bring your milk to simmer. So yeah, starches, I mentioned starches come in several different forms. It depends on the plant, where the starch is extracted from, whether it's a root vegetable, whether you have it from corn or other plants. Essentially, if we have chalk.
Yes.
Essentially, there are 2 forms of starch. One has long, unbranched chains of sugars. So here you have saccharose all the way along. And other starches have lots of branches. When you heat this starch, it kind of recrystallizes very quickly, and you have water seeping out of it. If you heat this starch and let it set, it keeps its structure. So this is good for cake glazes, etc. This is if you want smooth creams, you eat right away. But each starch from whatever plant will have a mix of both types of starches, and the ratio will determine the structure of what you get. If you cook starch just with water, some starches will give an absolutely transparent solid. This is cornstarch. This looks a bit milky, but it's a solid thing, just like our pudding. This is starch and water, and this is essentially starch and milk. The point at which starches gelatinize is also different for individual starches, but it's somewhere between 70 and 80 degrees centigrade. If you cook it above that point, the starch gets stringy, and the mouthfeel of whatever you're cooking won't be great. Not sure this pot works on this. So, if this could be washed. I know, yeah. I actually don't need it.
Oh, you don't need it?
Because it doesn't work. Sorry about that. So our middle layer as a cheesecake will have this whole lot of starch together with milk, together with egg yolk, and quark, and the starch will set the cheesecake. You want this kind of starch in there, which I think have cornstarch is okay for most of the things. It's coming along. So I just wanted to cook that to demonstrate how quickly starch gelatinizes when you cook it. For those physicists who don't cook. There's another element in here that does gelatinization in a similar way starch does, but again it's proteins, and that element is egg yolk. So I was going to talk about custards as well, because the filling is in a way very custard-like. It's not really a custard. For a custard you would use hot milk and egg yolk, and use the hot milk to gelatinize the proteins in the egg yolk. And there's a lot that can go wrong there. But again, knowing the science behind, it informs the process, it informs, and you'll see that whatever you've done for centuries is the right thing. Now, another thing Professor Kurti said is always use thermometers. At Professor Kurti's time, he had a voltmeter and a long thermocouple, which he inserted into his food. So cooking a souffle for him, or even just heating up milk or water, was a science experiment with several big instruments on the table. Thankfully, the times have moved on. And we have very smart kitchen thermometers that can tell you if your stove is working or not.
We also did microwave cooking in the 1960s with enormous cloisters.
Yeah.
Long before
Yeah.
we all had microwaves in our own home.
Yeah.
He was a pioneer of that, but
Yeah.
with
Yeah.
rather impressive looking equipment.
I bet. Essentially radars, microwave radars, isn't it?
Yes, it was cooking with radar. That's
Yeah. so this pot works better. Milk is coming up to scalding point. Can you see inside this pot in some way?
Probably not.
Probably not. So this is the milk. I'll pour in the starch, and I need to keep stirring because starch granules sink to the bottom of the pot. And if they're exposed to the heat there, they gelatinize very quickly. If I'm not stirring, I'm getting terrible lumps. And now it looks like Icelandic mud. What do they call it? Mud volcano. Yeah, I always like that. Don't stick your fingers in there. So it's just seconds, but you need to cook it for about 2 minutes to get all of the starch gelatinized. If you don't do that, the starch curls back onto itself much further, and you get weeping. And it also might soften again. So this would be an after-school lunch, sometimes at the Krauss family. I'll just pour it into this one. So, Catherine, if you wouldn't mind, get this washed. It's hot, it's hot. Thank you. So I was mentioning egg yolk and custards and so on. So I'll very quickly whip up a custard, and I'll do it wrong. I'll curdle it, just to prove the concept. So if you make a custard, you essentially put egg yolk and milk together and heat it up. This again leads to the breaking of these sulfur bonds, of the bonds that hold your ball of wool in its shape, and freeze these bonds up to create huge networks. Interestingly, with custards, the slower you heat, the better this network will evolve. Short networks can evolve very quickly. If you heat it rapidly, you get some thickening. If you stop, the custard can get back to a fairly liquid state. I suppose anyone who made custard is familiar with these problems. If you heat it just a little bit too long, you get something like scrambled egg. And we'll see how quick that goes. Sorry. Here. So about quarter of a liter of water. I'll heat that up, and I'll prepare the egg yolks. So I'll try to use the egg whites later. So I'll try to keep them free from contamination. Of course, at home I probably would wash my hands from time to time. Beautiful eggs. So we'll add a little bit of sugar. Let's use just another bowl. And if everything goes well, this should make a nice custard, which curdles just as nicely. Where did I put the whisk? I think it's with Catherine.
Whisker.
I'll use a spoon. I'm breaking the egg yolks, mixing them with the sugar. And I'll prepare the control experiment. I'll make another custard. Oops. Oh. Oh no. Do I try to rescue this? No. And a bit of sugar. And what I'll do here is adding a little bit of starch. Just a tiny bit. In the patisserie world, the custard without starch is called crème anglaise, and the custard with starch is called crème patisserie. If you use just a tiny bit of starch, there's almost no difference in texture. Thank you. It's great. So this one is coming up. If we put the egg yolks right into boiling milk, they will curdle immediately. So in order to cook them, you do what's called tempering in the patisserie world. You take the boiling milk, pour a little bit of it into the egg yolk mixture to cool down the milk and heat up the yolks. That's called tempering. And then that goes into the rest of your milk. And then if you make this at home, you want to heat it slowly in order to get a nice creamy custard. Now we'll go a bit faster. We pretend to be impatient. And I'll have my little Nicholas Kurti in my mind, taking the temperature. So
90 degrees.
this is already 90 degrees centigrades. Sugar will increase the coagulation point of egg yolk. If you do egg yolk by itself, I think it's 74 degrees where it coagulates. I think Curty has also done experiments or was involved in cooking eggs to perfection during the time of salmonella problems, so that you have a an egg yolk that's runny and an egg white that's perfectly cooked. If you know the setting times of egg white and egg yolk, you can do that. So now our custard here is cooking. And
Now up to 99.
it's 99. Waiting for the scalding point again. What the starch does is it again raises the coagulation temperature of egg yolk, but it also stops egg yolk from coagulating so easily. So in addition to just the changing thermal properties of the egg yolk, there's a chemical change. You have starch molecules in between these strands of proteins, and to create this huge protein network to make a nice custard, the protein molecules have to somehow get around the starch, which makes it harder for them. So, but we still do the tempering process. And back in. Now the interesting thing about this is you have to cook this. You have to cook this for a couple of minutes because egg yolk and starch have a special relationship. I mentioned that before. Egg yolk has a protein that can cut starches into sugar. And that protein degrades at about 80 degrees centigrades. So you need to cook it for a while, otherwise we'll have a problem. So we are now at 98 degrees, it's bubbling. It's not coagulating, it's still nice and liquid. It's really boiling hard. And I'll take it off the fire like that. So, what a difference. Okay, I planned to make the middle layer with our 3 quarks and egg yolk, etc. But I think you get the idea. For our recipe, if we go back, we just put all the ingredients in one pot, stir, and pour it onto our yeasted base layer to cook. Let's have a look at these breads here. It's actually quite hard to see, but they have all risen very nicely. I think there are marked differences in some of the pots. Differences that are bigger than you would expect from just the difference in making the dough. So I think that's egg yolk and that's sugar, I think. So really big differences. The top. Well, the top is some kind of souffle. Ideally, a souffle is very fluffy and light. Our recipe makes it harder to stay light because we add all that butter. So essentially a souffle with added butter, which will compress a little bit. There are some German baking wizards who can keep the topping very fluffy. I don't know what recipe they use. I don't think they use mine, but it is very tasty. The structure is souffle, and we allow it to compress at the end. The important thing with the souffle is the egg white, obviously. Whipped egg white, meringue, aerates the souffle. And during baking, of the souffle, we want to keep that structure. We want to denaturate the egg white, the albumin in the egg white, harden, and maintain its cell structure. So you have all these cells, bubbles, not like in an open sponge you use to wash your car. It's more, like in a bread dough or in some kind of froth. Hey, I'm losing parts. So egg white is really a special material in that it allows us to do that. So how does that happen? The albumin, the protein in egg white, denaturates when you add heat, when you fry an egg. The point is slightly lower than in egg yolk. That's why you can do these fancy anti-salmonella eggs. But it can also denaturate if you give it physical energy, similar to gluten. Gluten develops if you give it physical energy. If you beat it, if you put shear stress on it, gluten develops. Egg white develops a structure when you whisk it. And that's what I want to do now. This is getting a bit full. So we'll actually start with this one. It has egg yolk in it. Sorry about the noise. Anyway, while whisking, the whisks will beat air bubbles into the egg white, and at the same time, through the mechanical energy deposited in this egg white, it will denaturate. It will change its structure to something hard and persistent. The denaturated egg white is actually so hard and persistent that you can mix it in with egg yolk later. Only when you put egg yolk in before whisking it, it doesn't work. Or it's meant not to work. So, soft peaks, you would say. So, shall I do it? Yeah. Quite a different thing. You can over-whisk it, then these bubbles become so hard that they can't hold the water in their cell walls anymore, and the water will run out, and that's also undesirable. And the funny thing with this is, if we mix it in with other fats, egg yolks, butter, flour, it still keeps the structure if we are careful enough. And that's the famous folding in process. We are a bit pressed by time.
We should move on, yes.
Yeah, so I wanted to show you how to make the topping. I'll just fold in a little bit of my pre-made pudding to demonstrate how you can do it. So I'll also add an egg yolk, just for the sake of it. This one had a tiny bit of egg yolk in it. I'll put one egg yolk in here, and some of the pudding, also quite strange material. You wouldn't want to mess about with this egg white. And then the idea of folding in is that you gently break up the foam without necessarily destroying these bubbles. And that gives you a good base to make some spongy things like a souffle or a genuise. Genuise is essentially just egg, beaten egg white mixed in with egg yolk and a tiny bit of starch. So that's it. And it has more of a structure than this one. I think that's for the topping. Initially, I wanted to mix up the topping and bake it, but again, the topping by itself bakes in about 20 minutes. I verified that at home. And we should come to the last bit, which is putting it all together. Well, there it says heat transfer. Let's start off some heat transfer operations. This bread dough is not ideal for baking. If we wanted to have bread for supper, this wouldn't be a great thing. Also, 5 out of the 6 pots lack salt, so the bread would taste very odd. But the purpose here is not to make nice edible bread, it's to show something which hopefully will be apparent. I'll transfer these pots into the heat. Is that heat transfer? Yes. So I've got numbers on them. Hopefully they won't burn off. Okay. There we go. Do we have to press on again? No, it's coming. Good. Bake it for about 20 minutes or so. Can we keep an eye on the clock? It's not that critical. Bread is baking. Wonderful. Heat transfer, yes. Baking means we put it into something hot. The something hot is the oven. Our oven is, in essence, does that? Yeah. A black body cavity. So physicists like to look at that. You have got infrared radiation from all over. And in the middle, you have your cake. In the ideal world, the cavity is uniform. Means your cake gets the same amount of radiation from everywhere. We don't live in an ideal world, and the makers of ovens have their own ideas. So you get hot spots. What you get in domestic ovens are these rack holders. Well, they heat up. They're closer to your cake. They have pointy edges. All that affects how radiation is transmitted into your oven cavity. You have got a fan at the back, even if you don't use that fan. That's kind of a grill which has bumps and notches and screws and other materials in it. You might have a self-cleaning bottom. All these materials have different radiation characteristics, and you can't expect that your cake gets the same amount of heat from wherever you look. Plus, there's convection. So you have the heat at the bottom. You also have heat up here. In a normal convection oven. Usually up here it's cooler. Insulation at the top is not great, and what comes down is radiation. You have a heat element down here which heats up the bottom of your oven, and you get this kind of roll of hot air going in your oven. Depending how you are loading your oven, this roll will be distorted. Some spots might get hot air, some spots might not. If you have a fan oven, you have the same problem, only that this convection roll, but it's not a convection roll, it's a forced roll of hot air that will circulate in your oven. But you have to consider the aerodynamics of your cake or whatever you put in there. On Tuesday, who watched Bake Off on Tuesday? You remember Rebs? Her sponges didn't bake. So what she did is she had fairly high sponge tins and put them right underneath each other. You have a fan oven, the Neff oven do that create vertical sheets of circulating air, which is brilliant if you have flat trays and you want to bake them at the same time. In those ovens, you can bake something savory on the bottom, something sweet on the top, and the flavors won't interfere because the hot air circulates in vertical sheets. But if you consider that, you don't get air in here from the top, and you don't get hot air in here from the bottom. So you get heat transfer mostly into the top and into the bottom. So in the middle, you have a zone that won't get the air it needs to bake. So it's really useful to look at your oven in that way. And if you haven't, get an oven thermometer. They're pretty cheap. Put them into different places in your oven when you're baking, and you'll probably be surprised what different temperature readings you're getting there. One pretty famous book about the physics or technology of baking has a textbook that has a lot of experiments in it. First experiment you make 3 sheets of sugar cookies. And you bake these sugar cookies in your oven, and you take them out and look at the browning, at the coloration of these cookies to understand how your oven heats. So that's really a huge point. And I think that's the strongest physics point in this presentation, actually. Get to know your oven. The next point concerns failure. I mentioned at the beginning that my cake went wrong. I think I did 6 tries of this cake, different recipes. It got better, but each time something else was wrong. I didn't have problems setting the yeast base, that always worked, but I had problems with the topping and with the middle layer, and it was always underbaked, but it was to different degrees. So sometimes there was a problem with heat transfer, sometimes there was a different problem. And I'll talk about that different problem now. As a cook at home, especially if you try out things, you want to taste them. Yeah. I have to admit, sometimes I'm very bad, and I might lick my finger. So I might wash my finger, I might just brush something off, and then try something else. Now, whatever gets onto my finger there and egg yolk have something in common. And that's an enzyme that can cut starches into sugars. I mentioned that before quite a few times, amylase. And the amylase in spit is a lot more powerful than the amylase in egg yolk. But I'll demonstrate it with egg yolk. We have this beautifully set bit of starch, which I showed before. I'll add some egg yolk. And I'll stir just a bit, not too much, so it still has a good wobble and a good structure. So, and we'll see what happens with that. That was one of the problems, or a major contributing problem to why I got runny cakes in the center. Once I fixed that, I still had the problem that it seemed underbaked in the middle. So what is this cake I'm talking about all about? We have got Eierschecke. We have got, let's do it like that. We have got bread. At the bottom, we have got the belt, which is a cheesecake. And we have got a souffle on top. This is dense. This is a foam. And this is a foam. In terms of physics, both the souffle and the bread is a closed cellular foam. Now, foams are used in your house for insulation. Why on earth would someone pack a cheesecake between two thermal insulators? Well, they have done it and it's tasty. So there's reason. But to understand why bread or souffle or other foams are not so good at conducting heat, I'll just look at how a foam conducts heat. So I've got my bread here. Oops, or my souffle. We've got heat coming from here. And we have going heat out here, because this side is colder. So this is maybe the bottom of the tin, and this is somewhere near the cheesecake bit in the middle. So what happens in one of these cells is rather crazy. This cell wall is warmer than this one. So I'll just do that with plus and minus. In order for heat to get from here to there, the gas that's trapped in between has to conduct this heat. So thermal conductivity. We kind of know about that. We know that if we have a bath and run the hot tub at one end and switch it off, it takes a long time to get that water warm on the other side if we don't stir it. So we have conductivity, heat conductivity. Then we also can have convection in there. That means that inside the gas bubble, there's air moving, vortices, essentially like stirring the bath in a way. And we have radiation, because this wall is warm. It irradiates this wall with infrared. This is cooler, it still will irradiate back, but the energy balance is towards the cold side. And then we have something that acts against it, which is condensation. It cools this side, because steam, which is heated up here, will condense on this side and create water droplets on the wall. All these bits act together. The overarching bit is conduction and radiation, from what I've read. And the effect can be, well, bread, thermal conductivity is the same, similar conductivity to air, plain air. And that's about an order of magnitude less than a solid, than your cheesecake. So yeah, why on earth would you pack a cheesecake between two thermal insulators? And how on earth can you bake that? Simple answer, do it slowly. You bake this cake on a low heat. A souffle or a cheesecake you can bake in a bain-marie. I haven't tried baking this cake in a bain-marie, which is essentially hot water. I don't know what it would do to the yeasted base. It might not bake through. But bake it slowly on a lowest temperature for a long time. And then in order to get still a nice texture of the souffle, let it cool inside the oven. And with all of that and all of the understanding I told you about in this lecture, I managed to get a proper Eierschecke.
Wonderful.
And
That's maybe a good
that's
point.
it.
A good point to finish. So I guess the baking in the oven we can look at.
We can look at in 10 minutes. 10 minutes. They look somewhat different, don't they? Number 1 is pretty firm. Number 2 has somehow risen more and has this typical underproofed crack. That's the one with salt. So it looks like this one has proofed nicely. Salt has made it to proof slower. Therefore, it's underproofed. It has this crack. Number 3 with butter has clearly a much smoother skin. The one with sugar has a brownish skin. Obviously, there's more caramelization. Egg yolk also has a brown skin. That's probably an effect of this starch-eating protein that cuts starch into sugars. So we have more sugar available for the Maillard reaction. And this one is with egg white, which is very bouncy as well. Even more bouncy than the one just with yeast. The last thing we then should look at is this egg yolk starch mix. I don't know if you can see it, but it looks at the top as if, it's become a sludge rather than something that holds together. So introduce egg yolk into something starchy, and if you don't cook it, it will dissolve and go wrong. So there's the answer.